Hey there, Seahawks. It's Miss Adams, and in this video, we're going to go over the normal model and standardizing. All right, so standardizing allows us to compare one observation to another if they don't have the same parameters, meaning the mean and the standard deviation. All right, so we would make the mean become 0 and the standard deviation become 1 for both data sets, and then we can compare them. So we do this by getting a z-score. Z is x minus x bar over s, where x bar is your sample mean and s is your sample standard deviation. Or if we have the population statistics, then z is calculated by x minus mu over sigma, where mu represents the population mean and sigma represents the population standard deviation. All right, so this helps us compare by telling us how many standard deviations an observation is above or below the mean. All right, and so canceling out the units gives us an idea of how common the values are or how unlikely it is. If we get an absolute value of z that's greater than 2, so that means it's more than 2 standard deviations away, we typically consider that very unlikely. All right, an example, the height of 18 to 24-year-old women have a mean of 64.5 inches and a standard deviation of 2.5 inches. We know a woman that is 69 inches tall. How does she compare to the rest of the women in her age group? Calculate her z-score and interpret what it means. All right, so we're going to get her z-score. All right, we're assuming these other statistics are for the population of 18 to 24-year-old women. So we're going to do x minus mu over sigma. X is the woman that we know's height, which is 69, minus mu is the mean. The mean for women in that age group is 64.5, over sigma is the standard deviation, which is 2.5. And when I calculate that, I get 1.8. So that means the woman's height is 1.8 standard deviations above the average height of women her age. All right, another one. We also know a man that is 71 inches tall. Who is taller relatively? Men are known to be distributed with a mean of 67 inches and a standard deviation of 2.3 inches. So we're going to get the z-score for this man, x minus mu over sigma. So he's 71 inches tall. The mean for men is 67 inches, and the standard deviation for men is 2.3 inches. So when I do that, I get 1.739. So he actually has a lower z-score. So the woman is slightly taller relative to gender. All right. In a distribution of heights in a school, the mean is 66 inches with a standard deviation of 2.8 inches. Which is more unusual, a student with a height of 63 inches or 73 inches? Okay. So my z-score, I'm going to get for both of them. So 63 minus the mean of 66 divided by the standard deviation of 2.8 would give me a z-score of negative 1.071. And then for the 73, I do 73 minus 66 over 2.8, which gives me a z-score of 2.5. Okay, so the student that is 73 inches tall is more unlikely because the absolute value of their z-score is greater. Their height is further from the mean. To be certain that you would be accepted to college, you would need an SAT score of at least 1900. However, you took the ACT. What score would you need to get on the ACT to be accepted? So for the SAT, the mean is 1500 with a standard deviation of 250. And for the ACT, the mean is 20.8 with a standard deviation of 4.8. All right, so for the SAT, I'm going to get the z-score. We want 1900 minus the mean divided by the standard deviation. That'd be 1.6. So I want to have the same z-score on the ACT, and I need to figure out what score I would need to get. So I'm going to set it equal to 1.6, the z-score. I don't know what my x value is. That's what I'm trying to figure out. But I know the mean and the standard deviation for the ACT. And so then I would just do some algebra, multiply both sides by 4.8 and add 20.8, and I get x equals 28.48. All right, the normal model. The normal model or distribution is a bell-shaped curve that can be used when data is symmetric and unimodal. All right, it's a theoretical model, so it's not meant to fit the data exactly. So that histogram, you can see some of the bars are a little bit below that curve. Some of them are above, okay? But theoretically, it's unimodal and symmetric. Okay, remember, so if you kind of squint and look back, does it look like a mound-shaped that's you could fold down the middle? All right, so we have sample statistics and parameters. Parameters. Parameters are for the population, and sample statistics are for a sample. All right, and these are just the symbols that we would use. So when we're dealing with a sample, the mean, we call it x bar. The standard deviation, we just call it s. And some of the graphs would be like a box plot or a histogram or a dot plot, any of the ones we've used kind of so far. Parameter, the mean we say is mu. The standard deviation is sigma. And the graph would look like a smooth curve. All right, so your bell-shaped curve, this normal model, we're going to label it. So my mean would go in the center, mu, and then I would add one standard deviation to the right. I would subtract one standard deviation to the left. Then I would add another standard deviation to both sides and another standard deviation to both sides. And the notation, we use a capital N and then in parentheses, mu, comma, sigma. So the mean and then the standard deviation. The empirical rule. In a normal distribution with a mean of mu and a standard deviation of sigma, okay, there's this rule that tells us about how much percent falls in between each set of standard deviations. So 68% of the data falls within one standard deviation above or below the mean. So the mean plus or minus one standard deviation. 95% of the observations fall within two standard deviations. So the mean plus or minus two standard deviations. And 99.7% of the observations fall within three standard deviations of the mean. So the mean plus or minus three standard deviations. All right, normal percentile. So if you're finding the normal percentile without a calculator, you would have to convert the data into a z-score. And then you'd have to use a z-table. So the z-table is something you'll get with your reference sheet when you take the AP exam. And I also have some in class that you can use if you're not going to use the calculator. So you'd get your z-score. Let's say I have a z-score of 1.80. And you would look at your chart. So they have values across the top and along the side. So along the side you go to 1.8, and on the top you go to 0.00. And then you would match them up, and you would get a percent of 0.9641, so 96.41%. If you're using it with a calculator, you do not have to convert it to a z-score first, but you still might want to just to kind of have that as some work. But you would hit second distributions and then normal CDF, and then you would put in your lower bound, upper bound, mean, and standard deviation. So LB stands for lower bound, UB stands for upper bound, mean, and standard deviation. All right, if you are working backwards, so you have the percent and you're trying to figure out what that z-score was. So finding the z-score from a percent can be done by using the tables in reverse. So you would find the closest percentage on your table in the middle area. And then once you find it, you would go up and over and put those pieces together to make your z-score. Or in your calculator, it would be the inverse norm function. And then exact percentiles might not actually be in your table, so you're just going to have to pick the closest one. And when you do use your calculator, the inverse norm is always taking it from the left. So if you have that normal curve, it's always the values that are lower is what it's taking it from. All right. Suppose scores on an IQ test can be modeled normally with a mean of 100 points and a standard deviation of 16 points. Draw and label this normal model. So I'm going to label it as N for normal model with a mean of 100 and a standard deviation of 16. So that's the notation to let everybody know that you're working with a normal model. All right, so my mean is 100. It's going to go right in the center. and then 16 is my standard deviation. So I'm going to add 16 and go over 1. So my first 1 standard deviation over is going to be 116. I'm going to subtract 16 and go over to the left, and I'd get 84. Then I'd add 16 2 times to 100. So 2 standard deviations of 16 would give me 132. If I subtract 2 standard deviations of 16, I'd be at 68. And then 3 times the standard deviation plus the mean, 3 times the standard deviation minus the mean. All right, so there's my normal model. What percent of people scored over 123? So I'm going to get my z-score. My number in question is 123. The mean was 100. The standard deviation was 16. So that gives me 1.4375. So the probability that x is less than 123 is 0.9251. Okay, if you use a calculator or if you use the z-table. The probability that x is greater than 123 would be 1 minus 0.9251. Okay, so if you use the z-table, it's only going to give you the value that less than. Okay, so you'd have to find the greater than. So we would say 7.49% of people scored over 123. Okay, and this is if I didn't use my calculator. I could do it differently. If I plugged it into my calculator, I would put my lower bound of 123. My upper bound would be like positive infinity. We can't put that in our calculator, so we would just put 9,999,999. A really, really large number. And then the next question, what percent of people scored under 94? So 94 minus 100 over 16. That gives me a z-score of negative 0.375. So the probability that x is less than 94 will be 0.3520. So I found that z-score on my table and I matched it up. So 35.2% scored under 94. All right, on these we're going to do it in your calculator. What percent of people scored between 90 and 100? So I have my normal model with a mean of 100 and a standard deviation of 16. And I drew my normal model. Okay, so that's part of showing your work. Drawing and kind of sketching, I would put the mean and I would put at least 1 standard deviation above, 1 standard deviation below. Have those labeled. And then I want to go from 90 to 100. So I shaded that, I filled it in, and I'm going to find the probability that x is between 90 and 110. So in your calculator, you would go to normal CDF, so second distributions, normal CDF. And I would do 90 as my lower bound, 110 as my upper bound, 100 as my mean, and 16 as my standard deviation. And I would get 0.4680. So 46.8% of people scored between a 90 and a 110. What is the chance that someone scored over 120? So again, I have a normal model with a mean of 100 and a standard deviation of 16. I'm going to draw it, and I'm going over 120. So I'm going to go to 120, and I'm going to shade everything that's above it. And then in my calculator, I would do normal CDF, a lower bound of 120, an upper bound of a really large number, 9999999, and then my mean of 100, my standard deviation of 16, and I would get 10.56%. And I want to make sure that you write the work, so it's the probability that x is greater than 120, and then put the number you get from your calculator. What is the chance that someone scores less than 80? So again, I have a normal model with a mean of 100 and a standard deviation of 16. I'm going to draw my normal model. I'm going to go to 80, and I'm saying less than, so everything below 80 I would shade in. The probability that x is less than 80 is 10.56%. And again, you would go in your calculator, second distributions, normal CDF. Your lower bound would be this time negative 99999. Your upper bound would be 80. Your mean would be 100. And your standard deviation would be 16. Or you could find the z-score and use the table. Okay. All right. Blood pressure of high school students are normally distributed with a mean of 170 and a standard deviation of 30. Sketch the normal curve. So the mean is 170, that's going to go in the middle. The standard deviation is 30, so I'm going to add 30 each time for each standard deviation above. And I'm going to subtract 30 each time for each standard deviation below the mean. What is the probability that a randomly selected high school student has a blood pressure of 180 or above? So again, I have a normal model with a mean of 170 and a standard deviation of 30. I'm going to draw it, label some of it. Above 180, so I'm going to go to 180, I'm going to shade above. The probability that x is greater than or equal to 180 is 0.3694. So I did normal CDF, a lower bound of 180, an upper bound of 99999, a mean of 170, and a standard deviation of 30. So we would say 36.94% of students have a blood pressure of 180 or more. What is the probability that a high school student has a blood pressure of between 160 and 230? So I want you to try this one and put all the parts. The answer is 60.78%. Okay, but I want you to have all the other parts, and I'm going to be looking for that when we're in class. Number 4, what blood pressure has 25% of the observations below it? All right, so this is kind of where we're going to work backwards. So my normal model with a mean of 170 and a standard deviation of 30. So here's my picture. I can't quite fill it in yet, but we would do inverse norm. So second distributions and then find inverse norm. All right, we know the percent and we're trying to find the value. So my percent is 0.25. My mean is 170 and my standard deviation is 30. So the probability that x is less than some number, it has to be equal to 0.25 because that's the percentage that we get. And if I plug it in my calculator, I get 149.765. So I go to that point and then 25% of the observations fall below that value. What blood pressure has 60% of the data above it? So same model. I want the probability that x is less than some number would be equal to 40%. Okay, 60% lie above it, which means 40% lie below it. An inverse norm can only calculate the tail on the left. So that left tail would be shaded. All right. When I plug it in my calculator, inverse norm, 0.40, 170, and 30, I get 162.4. So 162.4, 40% are below it, which means 60% are above it. That one's a little bit trickier. All right, what is the IQR of the blood pressures? So IQR, we would need to find the 25th percentile and the 75th percentile. So it's a normal model with a mean of 170 and a standard deviation of 30. We need the probability that x is less than quartile 3, which would be 0.75%. So we need to figure out what value is quartile 3. And so if I do inverse norm, 0.75, 170, and 30, I get 190.235. And then quartile 1, what's the values that x is less than quartile 1? I have to set that equal to 25% because quartile 1 would be at 25% mark. And if I plug that in, 0.25, 170, and 30 into my inverse norm, I get 149.765. So my model, I would be at quartile 3 and quartile 1. And everything, all of this is giving me the value below those quartiles. So if I do the IQR, it would be quartile 3 minus quartile 1. And I would end up with 40.47.